Okay, light lecture today. I guess people are taking spring break a little bit early. So, questions or comments about the class? Alright, so before we start a new topic, I wanted to just wrap up what we were talking about last lecture. And thanks to Amin for pointing this out to me. So last lecture, we talked about the gain bandwidth product of this current feedback amp. And it seemed like just without doing too much analysis, you can get an arbitrarily large gain bandwidth product. So let's actually look at this a little bit more carefully and see what we can get. So remember, so for a current feedback amplifier, the input stage is just a buffer, a unity gain buffer. And we use a Darlington stage here because we want to get a high input impedance, as high of an input impedance as possible. And then we basically, this buffer is going to drive some external resistor, generate a current. We take that current and we mirror it into a high impedance node where we have a compensation capacitance. And then finally we have another buffer stage, and this is our output. So this is V plus, this is V minus. Incidentally, definitely you want to make this buffer high impedance buffer. So this Darlington stage is also very useful here. In fact, it's probably more important here. Why is that? Anybody? Debo, you haven't spoken in a while.
You wanted to fix your dominant pole, so you need a high impedance also.
Yeah, not just your dominant pole, but your DC gain, right? So if you actually have a weak buffer here and you end up loading this node, you reduce the gain dramatically. So we're going in, into great lengths to ensure that we have high output impedance. So here we use Wilson current sources. And then if we just put an emitter follower here, we're going to lose all that gain, right, by the loading effects. All right. So last lecture we calculated the loop gain of this, and we found that the loop gain is Z over R2, where R2 is basically this resistor. So in a feedback configuration, we would have R2 and R1. And Z is the impedance of this node. So Z is the impedance looking here, including this capacitor, obviously. So, and we worked out that if you assume that Z is just a single dominant pole, then what we get is a transfer function that looks like this. I won't rederive it. I think we derived it last lecture. So R0 is the real part of Z over R2, and then we have a single dominant pole, and the location of that pole is simply CL times R0. Okay, so that's pretty intuitive, right? Any questions? All right, also, if we're interested in the unity gain frequency, right, we set the loop gain equal to 1 and solve. So we have R0 over R2, approximately omega 0 over omega t. And so we have that omega t is omega 0 R0 over R2, or it's equal to 1 over CL times R2. All right. Now likewise, last lecture we derived the closed loop gain, is the exact gain, right? 1 over the feedback factor, plus 1 over 1 plus 1 over t. And if we substitute, we get, again, that 1 over the feedback factor. If we multiply this out, we get R2 over R naught, 1 plus j omega over omega naught. This is just 1 over t here. And if I assume that, just as we did last lecture, that R2 is much less than R naught, because I assume I have large loop gain at DC, then this simplifies to 1 plus R2 over R naught, 1 plus j omega omega 0 R2 R naught. And I can write this as the DC gain plus the 3 dB bandwidth of the amplifier, omega A. And so omega A is R2 R0 over R2 times omega naught, or 1 over R2 times CL, which is in fact the unity gain frequency that we just previously calculated, right? Omega t. Okay, so this shows very clearly that this amplifier has a gain bandwidth product. Let's just say the amplifier has a bandwidth which is always approximately omega t, right? And because this is only a function of R2, then we can see that R2 controls the bandwidth. So that gain and bandwidth are decoupled. So I think this is the important point, that the gain and bandwidth are decoupled. Now, in terms of raw performance, we're going to also calculate, what's the best we could do with this, right? So what's the best gain bandwidth product we could get? So we'll come back to that. But just this decoupling, what's the big deal about decoupling gain and bandwidth? What's good about that? Let's say at the end of the day you got the same gain bandwidth product out of this amplifier as you would a voltage feedback traditional amplifier. What are some nice features of decoupling the gain and bandwidth? I'll give you one hint. Imagine you're a customer and you're buying this amplifier from somebody who's fabricated for you, right? Why would you be happy if gain and bandwidth are decoupled? It's just nice, right? You select R2, that selects the bandwidth, and then you're always going to get this bandwidth out of the amplifier no matter what feedback factor you use. If you're using a voltage feedback amplifier, right, you know that the more gain you want, the less bandwidth you're going to get. Okay? So it's just nice to know that no matter what gain setting I choose, I'm going to get the same bandwidth. Any particular kind of amplifier where that would be important? Anybody? Yeah.
Variable gain.
Yeah, very good. So this is very nice. Nice for VGA applications. Because in a VGA or a variable gain amplifier, we're varying the gain all the time, right? The amplifier might be in a feedback loop. And now if the bandwidth is constant, that means I can stabilize my loop with just one bandwidth setting, right? I know that the bandwidth is not going to vary considerably in different gain settings, and so now my feedback loop, I just have to worry about one pole. I don't have to worry about that pole moving around. Okay, so then the next question is, well, how good is this? What kind of gain bandwidth product can we get out? So let's multiply the gain, the closed loop gain times the bandwidth. So the closed loop gain, the peak value is 1 plus R2 over R1, and the bandwidth we found to be R0, R2 over omega naught. And if I assume that this is much bigger than 1, this term here, the R2's cancel out and I get R0 over R1 omega naught. And remember, omega naught is just the capacitance at the high Z node times R naught. So actually R naught cancels out, and I get a nice expression, which is that the gain bandwidth product is 1 over R1 divided by CL. Okay, so this kind of looks familiar, right? It looks like a transconductance over capacitance. For a voltage amplifier, again, I won't do the math. You guys know very well that this is the closed loop gain. If you assume that the open loop gain has some bandwidth, you end up getting this expression. So this is the closed loop gain, and then the bandwidth is the bandwidth of the open loop amplifier times 1 plus A naught F. So here, the gain times the bandwidth is A naught 1 plus A naught F times omega naught 1 plus A naught F. This term cancels out. The gain bandwidth is A naught times omega naught, which is the unity gain frequency of the amplifier, which is GM over CL. Okay, so now we see that at least the answers are in very similar forms. The gain bandwidth product depends on this capacitance, right, which could be the same in both processes, and also some GM term. So how would you compare these two GM terms? Which one do you think you could make a lot bigger? Let's say I fix the power consumption of my amplifier. And I say for a given fixed power consumption, which topology is going to give me bigger gain bandwidth product? I mean,
I would think they're about be the same because R1 gets compared with 1 over GM as well, because the impedance of that node is 1 over GM about, so they're ordered the same.
Okay, very good point. So if you look at this regular GM stage, what really sets the GM we know is this current, right? For a given, so let's say this is a MOS amplifier. For a given current, for a given overdrive voltage and a given current, GM is fixed. Same for bipolar amplifier, right? GM is just proportional to this current. Now we have a voltage buffer, and it dissipates some current, and then we have a resistor. And so now you would say, okay, here, because my GM is inversely proportional to this resistance, I can just make this R very, very small and get very, very high GM, and therefore get very high gain bandwidth product. That's true until this resistance becomes comparable to the output resistance of this buffer. And as Amin pointed out, because this buffer is actually a follower, the output resistance is on the order of 1 over GM, right? And so that tells you that, yeah, you can only make this resistance as small as, let's say, on the order of this 1 over GM. Otherwise, you start losing gain. And if you do a more full analysis, you see that you start losing bandwidth too. So let's say I conservatively say this resistor should be 10 times bigger than 1 over GM. That pretty much sets the gain bandwidth product of your amplifier. Okay. Let's now talk about CMOS Class AB amplifiers. Now remember, the way we got this current feedback amplifier was a topology like this. We took two voltage buffers, put them across a resistor, generated a current, took that current, mirrored it to a high impedance node, and got some voltage gain out. And then at some point we thought, well, you know, if we get rid of this second buffer stage, we get a current feedback amplifier. If we keep it, we get a traditional voltage feedback amplifier. If you're driving a resistive load, you include a buffer. Otherwise, you don't include a buffer. The basic building blocks, so the class AB building blocks that we looked at is essentially it came down to a circuit like this, right? Some follower and some resistor. And if I try to build this with MOSFETs, right, I could also build this with MOSFETs and use this as a basic building block. You actually, if you use this, you realize, wait a minute, why do I even have this resistor here? Might as well just get rid of this resistor. It's not really doing much for me. I can't get rid of this resistor in the bipolar because then the input range would be very low, right? And it would actually, with a very small voltage, it would completely saturate out. So this resistor is necessary to get a decent input range. But here, I should mention, once one of the devices actually saturates out, then you stop getting the class AB action, right? Here, though, because the input range of these devices is very large, you can actually eliminate this resistor and just build a, so effectively, you know, with level shifters, just build a circuit like this, and because I'm using both polarities of devices, I can both source and sink current and use this as a basic building block to build a class AB input stage. Okay, so actually, sorry guys, I screwed up. This is my input voltage. So I'm applying my input voltage, right? I want to take this input voltage. I'm drawing a half circuit here. What I'm drawing now is actually this full circuit. So this is the N side, and this is the P side. So this basic building block is this one here. So I'm really applying my input voltage across this resistor. In a MOS version, I apply my input voltage across these two VGSs. If the input is positive, I draw current from this side, right? If the VGS is negative, I draw current from the opposite transistor, right? So I can both source and sink current. Okay, questions? Okay, so let me draw one particular incarnation of a class AB amplifier using CMOS. For simplicity, I'm going to draw simple mirrors with the understanding that if you want to get higher output impedance, of course you would use a cascode mirror. Better yet, a high swing cascode mirror. Okay, so the circuit is symmetric. And to understand how this circuit works, notice that what I have at the core here is really just a GM block. Okay, these are level shifters. And the way to see that is if I apply an input, that input gets applied across two CMOS class AB stages. It gets applied across here, these two VGSs, and it gets applied in the inverse polarity across these two VGSs. Okay, and so if I look at this picture, this is the GM stage, right? My input is a class AB input GM stage, and then the rest of the circuitry are just mirrors that copy the current to the output. And because this is a fully differential amplifier, I actually copy it to both sides. So if this is, say this is plus, this is minus, if I apply, let's say, a positive voltage step in this direction, the current would increase here, right? And this current would get mirrored to the output and flow into the load. How about from the other side? Well, from the other side, the current of this side decreases, right? And so that generates a current in this direction on the mirror, which gets copied to the output and then summed. So we can see that the outputs of these two GM generators are summed in parallel at the load. And likewise, over here, this current gets mirrored over here, this current gets mirrored over here, and so I'm pulling out twice the current from this capacitor. So this is the positive, since this terminal is actually going down, this is the negative output, so this is VON, and this is VOP. All right, questions or comments about this?
It's not entirely obvious to me why that resistor for the BJT makes it have a decent input range and why you don't need that.
That's a good question. So let's look at it. So essentially, I'm taking my input voltage and applying it across a delta VBE in this R. So let's assume this R is equal to 0. Then I'm applying my V input across basically two different VBEs, right? And this, what other circuit do you know that applies the input across two VBEs? Kind of like a diff pair, right? A diff pair does the same thing. The difference here is I'm using an NPN and a PNP. Well, what's the input range for a diff pair? How much voltage does it take to roughly steer all the current to one side or to the other? Order of magnitude, don't have to give me the exact number. Is it 10 millivolts? Is it a volt? Is it 5 volts? No, it's actually much lower. It's on the order of 100 millivolts, about 120 millivolts. It's just a few kT over Qs. So you have a very low, so if you look at the transfer characteristic of a diff pair, it's very sharp, right? It's this hyperbolic tan characteristic, and it's very sharp. So over hundreds of millivolts, it saturates. For MOS, automatically, right, it's like a kind of like a square root function, so it's much larger input range. All right, it's a good question. Okay, so how do we realize this in practice, right? What we need is we need some level shifters. And of course we could just use diode connected transistors as level shifters. I'll just draw half the circuit. And so let's call this M1, M5, M3, M7. So the nice thing about this circuit here is that it's a GM stage that's class AB. So this is the most important point, is that it's a class AB GM stage. In other words, the current actually never limits. As I increase my input voltage, let me just draw a simplified form. As I keep increasing, let's say, this voltage more and more, the VGS of this device just gets bigger and bigger. This device shuts off, and so all the current is coming from here. So on the positive side, this GM stage just keeps giving us more and more current. So this is IOD over V in. Likewise, on the negative side, eventually this device shuts off, and then this one just remains on, and this guy just keeps giving us current. Okay. So getting back to your question, so similar operation, right? As the input gets bigger and bigger, this device remains off, this device shuts off, and all the current just comes from this device. So you might ask, what if I, again, going back to the question of what if we didn't have this resistor here? This actually, I guess I was wrong. If we didn't have this resistor here, the circuit would still work fine. So going back to your question, even without this resistor, it would still be class AB. The problem is that it's very nonlinear, right? It would give us exponential current flow. So the GM stage would be too nonlinear. So the resistor is needed for linearity. Okay? Yes, I mean.
Just a general question about the class AB. So this would be quite similar to having a differential pair without the current source at the bottom.
Yeah, yeah.
And so there, the CMRR would be sacrificed. Is it the same case here?
No, because yeah, that's actually an excellent question. Let's come back to that question, because in fact you are right. So let me just come back and explain what your point is. So your point is that if I have a diff pair, the reason the current limits is because eventually the only current I have available to slew with is this bias current, right? As one device turns off, this is the only current I have. If I just ground, so if I have a pseudo differential pair and I just ground this node, then this current won't limit, right? Just like what I've drawn here, as the input gets larger and larger, this can supply more and more current. So the reason we don't do that, as we discussed, is that it reduces our common mode rejection, right? Not having a current source here. Another potential problem with this approach, is that there is a bias circuit that's on average forcing this current to be constant, right? And so if I apply a step input, I have to fight against that bias loop. And depending on the speed of that bias loop, it may actually limit the current if I slew too long. So it's not quite the same, because I can't, in this circuit, I have to tie this to some bias, right? And there is a time constant associated with establishing this bias current. It's not quite the same, but it is a similar effect. Incidentally, as voltages have gone down, as supply voltages have gone down, using the pseudo-differential topology has become a lot more popular. Just don't have the headroom to give up to the current source. All right, so how does this circuit work? Let's say more details, more large signal model. Well, it's actually very interesting. What you can show is that this transistor, this configuration, is really equivalent to a single transistor. So we'll call this the equivalent transistor. And to show that, first of all, you'll notice that let's assume it's square law. Okay, very simple model. And so the input voltage is VGSN plus VGSP. I'll just drop the absolute value signs. So it's VTN plus VTP plus 2I D mu C ox W over L N plus 2ID mu C ox W over LP. And if I kind of collect terms here, you can see that this looks a lot like another square law transistor where this is VT effective, and I can just lump all this together, right, and say that this is some effective mu C aux W over L. Right, functionally they're identical. I have threshold plus square root of current. So I can say that the input voltage is VT effective plus 2ID K prime W over L, the whole thing effective square root. Okay, questions or comments? So this cell here really acts like a square law transistor in long channel regime. Okay, I'm going to skip some of the biasing details. It's not that interesting. One interesting point is the frequency response, so let's talk about that. Alright, so let's look at this amplifier and comment on its frequency response. Okay, so where are the dominant poles and the non-dominant poles for this circuit? How about Vikas in the back?
Would the dominant pole be at the output?
Yeah, that's the dominant pole, right? How about the non-dominant poles?
My guess would be at the NMOS and the PMOS and center of the circuit.
That's a good guess, yeah. So potentially this node could be a non-dominant pole, right? Its impedance, so the capacitance here is, the CGSs of these devices. The impedances are like 1 over GMs of these devices. So if we're running these in low current, that could be our non-dominant pole. Also, I don't have to make this a unity gain mirror, right? I could actually have a current step here, let's say 1 to K. If this mirror has a step 1 to K, what's its frequency response? It's about Ft over K, right? Ft of the transistor over K. And so because these are PMOS devices, probably this would be my non-dominant pole, Ft over K. But if I'm not careful, I can easily have the input limiting my performance. In particular, looking at this circuit, can someone say under what conditions would the input completely dominate over the mirror? If you're not careful. Let's say you're given this schematic and you've got to lay it out. And so you're laying it out. When you lay things out, you think about issues. What are you going to do to the body connection of these transistors? So you have an option to triple well process. So you can choose whatever node you want for both the NMOS and PMOS. Where would you tie the body connections? Well, your first instinct is get rid of body effect, right? So you would just do this, right? Is that a good idea?
It adds a lot of capacitance from the well.
Right. So now you have a huge, this capacitor now gets bigger. This is our well capacitance. So apparently it wasn't such a good idea. We're probably going to tie these to ground. If you tie them to ground, though, are we going to have problems with the body effect? In other words, if this source voltage moves, right, that generates a current in opposite polarity to the GM, so it's going to reduce the gain. Okay. I mean,
Can't you just tie the bodies to the opposite pole, so you get the twice the effect, 2 GMs?
you
So
can do that. It has some stability concerns. It's actually positive feedback, but it is done. People have tried it. So the idea is that I could take the body connection here, and you want to tie it where? You want to tie it to this source? You could do that, but you still are going to load this node, right? So I'm going to, where are you going to tie it? You're going to tie it over here? Okay, so let's say I tie it over here. Yeah, that's actually good, because not only do you get rid of this gain reduction, you actually boost the gain. So now GMB adds to GM. But you still get well capacitance, right? Yeah. So you're right. This option, so if I do this, this helps gain, but I still have this frequency response issue. So it looks like I'm just going to have to live with a gain reduction. Anyone think of a way to not have this well capacitance but still have the same gain without the body effect? I'll give you guys a hint. How are you going to size these transistors? Anybody? Well, remember, this is a differential circuit. Did someone have a idea? Yeah.
You size it for equal VD sets so the swing both sides are equal.
How does that help?
So your excursion out both ways, it linearizes it. I don't know, equal VD sets.
Okay, but we're talking about frequency response, right? How does that help frequency response? You're actually onto something. Why does that help frequency response? Well, it creates a virtual ground, right? If I actually drive this circuit, this is a differential circuit. If they're sized to have the same GM, this point doesn't move, and so I have a virtual ground, and then this capacitance doesn't matter. All right. So what I want to do is equalize the GMs. Okay, so this is a great circuit, but probably won't work for your project. Why is that? Now, it looks great, right? I have dominant pole, maybe non-dominant pole from this current mirror, Class AB input stage, really fast slewing. Why can't I use it? You should try. Maybe you can get it to work. My guess is you probably won't get it to work. Any reason? It does require a lot of headroom, right? You've got lots of transistors in series here, stacked of 4 transistors. So give it a shot. It might be interesting to see what kind of headroom you can get out of this. But probably this won't work below 3 volts or so. The other issue is these level shifters, they seem innocuous, right? They're just little batteries here. But what's the problem with a real level shifter? Yeah, it adds power. I actually have to, with a real diode, I have to add a current source here, right? What else?
Is it going to dump noise into your input?
Yeah, noise. Yeah, this is going to be noisy. Okay, look at some other amplifiers just so to give you some more ideas for your project. A very similar op amp is called a current mirror op amp. And it's actually just what we talked about. There's a GM stage, and then you have mirrors, and you dump it to the output. Let's say in a single-ended version of the output, or in a fully differential version, this would be the plus side, this would be the minus side. And so I can use, again, a traditional input stage. So this is not class AB, so it will have slew rate limitations. But it's actually going to be better, and we'll see why. So these are just bias voltages. Later on today we'll talk about how you might use this node for common mode feedback. And then these are my outputs. So let's see how this works. So these rectangles here are current mirrors. This is a mirror 1 to K, 1 to K. And let me call this plus, this minus. So if I apply a plus input, positive step input, this current increases, this current decreases, right? That means this current gets mirrored over K times bigger, and it flows into my output. So this is my positive output, and this is my negative output. Okay, why is this potentially better at slewing than our folded cascode? Anybody? Except Amin? Alright, Amin, you have some ideas?
I think you have a current gain of K, so K times more current gets to the output.
Yeah, it's very simple. I have this mirror that multiplies my current, I bias by K, and so slew rate is proportional to current. Great. We've looked at amplifiers very similar to this. The gain, the DC gain, is no different than all the others we've seen. You have a GM stage, you have a current gain stage, and then you have the output impedance, the high impedance node here. So again, it looks a lot like what we've studied before. How about the choice of, well, let's talk about the poles. Again, where do we think the non-dominant poles for this circuit are going to come from? Yeah, Christian?
Either the current mirror or the top of the diff pair.
Well, the top of the diff pair is a low impedance point, right, in the current mirror. So, in fact, that is part of the current mirror, right? So you're right, it's the current mirror. So this is the non-dominant pole. So the non-dominant pole comes from kind of the FT of the P-channel device divided by KT. So, you know, this circuit would work perfectly well if I had used a P-channel input, right? PMOS version, and mirrored upwards, right? What are some of the benefits, advantages, disadvantages using NMOS versus PMOS for the input stage? It's very similar to a folded cascode, right? So in folded cascode, I can have an NMOS input or a PMOS input. Which would you use? Okay,
Yeah,
Michael.
it's again the one way of noise for the PMOS is slower than.
How about frequency response? How would you compare frequency response? Which do you think is faster?
the NMOS? If I
Um,
would, I mean, in order to get the same GM, I need to blow up the PMOS.
well, what really set in these circuits? What's really setting your bandwidth? Is the dominant pole setting your bandwidth, or is it the non-dominant pole?
It's the dominant one.
But in terms of design, right? What are you limited by? If you try to make this higher and higher speed, at some point you run into a wall, right? That wall is a non-dominant pole. So which case is going to give you a higher non-dominant pole?
Yeah, it's with the PMOS input.
Yeah, because now you have an NMOS mirror. So an NMOS input stage has the advantage of having lower noise because the GMs are larger, right? But the PMOS input stage can give you higher bandwidth. And that's because of the current mirror, because we need the opposite polarity current mirror. Higher bandwidth due to current mirror, and this is due to the non-dominant pole. And then, as you mentioned, the flicker noise is going to be better for the PMOS. Alright, and that's also similar to the considerations of a folded cascode, because in a folded cascode, this also feeds into a cascode PMOS stage, right? And that sets your non-dominant pole. Okay, one of the issues with this amplifier is its slew rate properties. So we just said the slew rate limiting is good, but I'm going to show you that it also has a problem. So let's say the input voltage is so large that only this transistor remains on. So this transistor is off. So then I have a current mirror, and this current mirror is effectively not there because it's just off. And so this is a large step input voltage. This is IB, let's say. So all of IB gets mirrored over here. I have KIB flowing here. And what's the current in the other branch? Anybody? It's 0, right? Because there's no current flowing here. And because this is a fully differential output, I'm not taking this current, mirroring it over here, and driving. So this has the awkward property that it will slew on this side, but not slew on this side. Okay. So to fix that problem, I just have to add some more current mirrors, right? So what I'd like to do is to take this current, mirror it twice, and flow it over here. So here's a way of doing that. These circuits get fun to draw. So lots of current mirrors. This is why people ended up inventing a symbol for the current mirror, but I just don't like the symbol, so I don't use it. And I like the rectangle, but it's not that elegant. So what I'm going to do is I'm going to mirror. I'm going to have two mirrors, a 1 to N mirror and a 1 to K mirror. So the 1 to K mirror is our standard mirror. And then down here again I'm going to have another 1 to K mirror. So this is 1 to K. This is 1 to K. This is 1 to 1. and I take this current and I mirror it over. So now, when let's say we get into the same condition where I'm slew rate limiting, so I'm pulling all my current here and dumping it into the load here. Now I also take a copy of this current, mirror it over here, and pull it out of here. So now this will slew both directions symmetrically. Okay, questions? I'm sorry?
Are the two bottom devices in the middle diode connected?
Yeah.
Oh, okay.
Yeah, thank you. Yes.
What happens in the normal case when there's no string? Like you get double the current?
Yeah, so if there's no slewing, it all still works out, right? So all these arrows I've drawn. So use a different color pen. So under small signal conditions, right? This gets here, this gets copied over here, and this current gets mirrored over here, and then gets mirrored over here, so I end up getting twice the current. That helps the gain as well. Okay, here's another op amp. Another one for you. Back to the folded cascode. And for me, this op amp has a little bit of personal history, because when I did my project for this class about 10 years ago, this was the amplifier we ended up using. And the idea is, in a folded cascode, you have this decision of, should I make my input stage PMOS or NMOS, right? Why not do both? So this is my NMOS input stage. And then you have also a PMOS input stage. And then you got to figure out which ones are plus and minus. So if I put a plus step in here, right, that draws current in this direction, and so here the current is leaving, here the current is adding, so this node goes up. So this is the positive terminal. This is the negative terminal. To get the same effect here, I want current to actually come in this direction in order to add to the output and subtract from here. And to do that, I need to add a negative input here. So this is the minus, this is the plus. Does this terminal goes up? Yeah, that looks right. And of course, these are connected together. Okay. So what are some of the advantages and disadvantages of this over a normal cascode?
First thing I say is that you lose some phase margin right at the beginning because the NMOS and the PMOS have two different paths, and one is slower, one is fast, so you lose like 20 to 30 degrees of phase.
So yeah, so you are right. So one of the issues is you get an extra non-dominant pole. And of course, you can size things appropriately, right? So you can size things so that, let's say I get my non-dominant pole from my NMOS devices. And to start out with, my NMOS devices are a factor of 2 roughly faster. And then I can size them so they're a factor of 4 or 5 so that I don't, this sets the non-dominant pole. So if I'm going for pure speed, just trying to get the most speed possible, you're right. You're limited by the fact that you have 2 non-dominant poles. But usually you're not designing for pure speed, right? You're designing to meet specs. And transistors these days are so fast that you have a lot of flexibility when it comes for speed. Okay, good. So what are some of the other potential issues or advantages of this amplifier?
You can get like over the VDD input range.
Yeah, it has very good input range. So the idea is that normally if I just got rid of one of these guys, if the input goes positive, that's great. If it goes negative, this guy just shuts off, right? And the amplifier stops functioning. So my input common mode range on the low side is limited by this guy. But now, if I actually add a PMOS stage, it's the opposite. As the input gets low, as the input common mode gets low, this PMOS stage is happy and continues to function very well. So now I have a large input range over which both devices are active, right? Of course, one of the problems is that the GM will drop, right? Because I have 2 parallel paths, the GMs are adding. So my total gain is GMN plus GMP times Z, right? So if I just had one stage, on the positive side, right, I hit my limit because I saturate out my current source. I saturate out and I'm only going with one current source. On the negative side, though, I could get into a situation, if I haven't designed this right, where I actually saturate out because the input common range voltage is getting too low, right? Now, by adding the second stage, my gain is going to drop, right? So the slope of this curve changes, but the PMOS is still alive. And in fact, I can fix that problem by somehow increasing the current in the PMOS stage under this condition so that I get back roughly the same GM. Right? And then vice versa, right? If I go too high, the PMOS turns off and I can actually dynamically increase current on the NMOS side. So let me show you how we would do that without making it too messy. So what I'm going to do is just draw the input stage. So these guys go off. Let's say I have a very high input. And so my PMOS stage is basically turned off. So if the input common range is very high, these transistors turn off, and so I can steal the current of this guy mirror it and add it over here. And I can do the exact same thing over here. When this guy turns off, when these guys turn off, I can add another transistor to take this current, mirror it, and add it to here. And so if I design these right, this transistor will only activate when these transistors turn off, and it'll take this current, add it over here, so we get higher GM. So using this scheme, if you design things right, you can get the same GM over the entire input range from ground to VDD. Otherwise, it's just a lot like designing a regular folded cascode. So it's a double folded cascode. Okay, another practical topic which is very important, and it's actually needed in all the circuits, right? All the circuits that we've drawn simply wouldn't work without some kind of common mode feedback. And just to make the discussion simple, I think we've talked about this already a little bit. Let's take the world's simplest fully differential amplifier. Doesn't get any simpler than this, right? This amplifier simply will not work. And the reason it will not work is that if you build it, and then you go and you measure it in the lab, without common mode feedback, what you'll get is this will be what are you going to observe at the output? It's going to be either at VDD or ground, right? So why is that? Why is it that this thing doesn't work? Phil, why doesn't this work?
You need common mode feedback.
Why do we need it? Why do we need common mode feedback?
Need like an offset voltage. Separate issue.
Why do I need an offset? Let's say I'm designing this, and let's just say this is 100 microamps, and I bias this up to be 200 microamps. So if the input is 0, if the differential input is 0, differential output is 0 too, right? Circuit should work. So why introduce another feedback loop if you don't have to?
Because of like mismatch?
Yeah, exactly. So let's say instead of 200, this were 201. So what would happen to the circuit? Where would the common mode of the output be? Would it be plus or minus? Would it be VDD or VSS?
VDD.
You sure? Right, I'm pulling more current out of this node than I'm adding to it, right? So it would actually go to VSS, right? And the idea is that the voltage out here, delta V, is very sensitive to delta I because you have such a large output resistance. So for instance, in this case, if I have just a microamp, and let's say R big, let's just say it's a mega ohm, then delta V is a volt. So just 1 microamp, which is, right, 1 part in 200, 0.5%, will totally mess this up. So if I don't have 0.5% matching, I'm going to mess this up. Well, one approach you would say, well, you need better matching. Let's just build really good current mirrors, and let's get the matching to the point where instead of 1 volt, this is 100 millivolts. So well, it's not clear if that's possible, but let's say that you are just a really good engineer and you went in the lab and you banged away at the problem and you managed to get it down to 100 millivolts, right? Do you pat yourself on the back and say, God, I'm good, or is there still a problem? You're never going to get it down to millivolts, right? There's no way. The matching is never going to get better than, let's just say 0.1% or something. So what's the problem if the common mode range is unknown within 100 millivolts? Do you care?
Do you have to set a bias on the next stage?
I'm AC coupled to the next stage. I don't care, right? And my next stage is also differential, so it's rejecting the common mode anyway. So what's the problem?
having a common mode range that goes around changes the characteristic, the bias of your transistors. You did have
How so?
VDS.
Let's say I've biased this to be mid-rail, right? Where mid-rail is kind of the high gain point of my amplifier. What's the problem? Everything's, let's say nothing, I run it over process and temperature and nothing goes out of saturation. It's all fine. The only thing is that I don't know the common mode voltage here. I just know it within 100 millivolts. And the next stage is also differential. It's rejecting the common mode. It doesn't mess up the next stage. So what's the problem? Why not just be happy?
It'll it'll cut down on your differential output swing.
Yeah. You know, we don't have that much voltage headroom to play with, right? We might have 2 volts here. And maybe if we've designed everything just right, we're getting, let's say, 1.5 volts swing. So now if the swing is 1.5 plus or minus 100 millivolts, right? That's not good. Well, it's going to be minus always, right? So you're losing swing. So basically, even if this is 100 millivolts, you're going to lose swing. And if you had a 10 volt supply, you wouldn't care. But if you only have 2 volts, swing is very precious because it's dynamic range. The only way to win back that dynamic range is to dissipate power. So the idea is that we do need a feedback loop to fix the common mode voltage here, let's say within tens of millivolts or better, so that we don't really hurt our swing. So all I really need to do is take these 2 outputs, let's say sum them, multiply by 1/2, and that's the common mode voltage. That's a measure of, this is VO1, VO2. This would be 1/2 VO1 plus VO2. That's the actual common mode voltage, right? Because VO1 is V common mode plus delta V over 2. VO2 is V common mode minus delta V over 2, where this is a differential signal. If I just sum these signals and divide by 2, the differential cancels out and I just get the common mode signal. So here I have my common mode signal, and what's a good way to change the common mode of this circuit, right? What's a good knob to turn on this circuit? Oh, this is a particularly good knob, right? So if I now take this, compare it with the desired, let's just say V common mode D for desired, and then adjust this voltage to stabilize the common mode, I'm in business, right? Since this is an inverting stage, right, this is a feedback loop, since this is an inverting stage, I hook up my differential amplifier here, and I'm set. If the common mode is too high, this voltage, right, is bigger than this voltage, so I apply big voltage, that increases the current, which pulls this down low, and vice versa. So how am I going to do this? How am I going to detect, how am I going to build this adder? Any suggestions? So how to sense the common mode voltage? Because once I can sense it, I'm in business, right? Just build another little diff pair here, adjust this bias current, I'm done. So actually, the hard problem is how do you actually sense this voltage? So any suggestions? Okay, Vincent?
Can you just use 2 resistors and then tap in the middle?
Yeah, so this is probably one of the earliest techniques that people have used. You just use 2 equal value resistors. And in fact, if you look at this, maybe I don't even need this amplifier, right? Maybe I can just take this voltage, tie it directly to this point, because this is inverting. Come back to that. But, okay, so this is a common mode. This is going to sense my common mode, right? And the way it works is it's basically a voltage divider, right? If this is RR, say this is R1, this is R2, this is VO1, this is VO2, VCM is VO1 R2 over R1 plus R2 plus VO2 R1 over R1 plus R2, and if these are equal size resistors, it's just 1/2 VO1 plus VO2. That's nice because this voltage only depends on the average common mode voltage. If I have a differential voltage, right, this goes symmetrically up or symmetrically down, this point will not move. So this is not sensitive to a differential output, it's only sensitive to a common mode output. Okay? What's the problem with doing this? Would you do this? Anybody? Yeah, Michael?
Yeah, you're lowering the output. If
I
you
could just
make
make these big, right?
Yeah, then you have noise falling at the output.
If I make them big, I have noise problems. So let's just use mega ohm resistors. 10 mega ohms, right? What's the problem? If they're really large, they're not even there, right?
But you get capacitance.
So what?
Capacitance.
So what's wrong with capacitance?
Yeah, you're loading the differential output, right?
Yeah, you are loading the differential output. You're right. Let's say that you had a perfect process and you had these really nice resistors and they didn't have any capacitors. Would you use them? Would this be a good idea? Say someone in the device lab said, I have a way of bringing in resistors into a standard CMOS process, and they're really big. They're mega ohm per square, and they're tiny. They have no capacitance. Would this be a good approach? Anybody have an idea? Seems pretty good, right? Doesn't load the output. You have to make them really big, right? If the output impedance is 100 mega ohms, you got to make these a giga ohm, right? So you have these giga ohm resistors. They're not loading the output. They're sensing the common mode voltage. Any issues?
Does it rely too much on the matching of the resistors? That might not be perfect.
That's an issue. They do have to match, but it's not a huge issue. Well, the problem is speed, right? I mean, you alluded to it with it's going to not only load the differential, but there's got to be, at this common mode voltage, there's got to be capacitance, right? And that capacitance doesn't hurt our differential mode output, but it will slow down our common mode output. The time constant for this common mode detection circuit is R times C. So if R is too big, then the common mode slows down, right? If it's a giga ohm, it doesn't take much capacitance here to have second time constants, right? And then all of a sudden the amplifier needs a second to get the right common mode voltage. And in 1 second, the packet is gone, right? The packet came in 1 millisecond, and the whole time the amplifier was railed, it didn't detect the packet, right? So clearly we need a fast enough common mode loop. You can't arbitrarily use large resistors. So let's say I need to use small resistors. Anyone think of a way to get around that? Get around this problem. Somehow not load the output.
Fixed capacitance?
I want to use these resistors, right? Let's say I like resistors. I'm doing a continuous time circuit. Okay, you have a very good suggestion. We could use switch capacitors. But unfortunately it's a continuous time circuit. It's fully differential. how am I going to set the common mode without loading the output?
Looks like you need a buffer.
Yeah, why not? This is the business we're in. We're all circuit designers. All we do is move impedances around. So, okay, the output impedance is too high, so I'll buffer it. And now, this is my common mode sense. Is this going to work?
You lose the threshold voltage, but it depends on how much headroom you have available.
Yeah, you're absolutely right. It works, but it only works over a limited range, right? Before, I had gone to great pains to make my current mirror as high swing as possible, right? If I've designed the circuit, everything to get a really high swing, now I find out that, oh, I can't get that swing. I'm limited now by this circuitry here. So this could actually, this reduces the swing for the entire amplifier. And so we see that actually this issue of detecting a common mode signal is actually pretty tricky. It's not very easy to do. It seems like no matter what we do, we're either going to slow the amplifier down, we're going to add noise, or we're going to reduce the swing. And it's actually true. It's pretty tough. It's a very difficult problem to design a very good common mode circuit. Let me mention, so this approach here uses resistors. As we know, we kind of don't like resistors. They're not, in a typical CMOS process, they're not really available. So I'd rather not use resistors. So here's a circuit that doesn't use resistors. Actually just uses two diff pairs. So this is an all resistor common mode sense circuit. And so at the middle here I put in the desired common mode. Let's say it's 0, just for argument's sake. The observation is that, so these are PMOS diff pairs, and I tie my plus input and my minus input, so this is VO1, this is VO2. The idea is that if I have a differential signal, let's say this goes up, this goes down, then this generates a current in this direction, this goes down, so it generates a current in this direction, and if I, let's say, use this terminal, let's call this V common mode sense, this current just circulates, right? And so this voltage doesn't move in response to a differential signal. On the other hand, if I have a common mode signal, then both of these are going up, both currents are going up, and so they sum, and this voltage actually goes up. So this is sensitive to the common mode voltage. Likewise, if this goes down, this node goes down. So this is an all transistor method of detecting the common mode voltage, and I guess we'll save the rest for after spring break.